Welcome to PG Pathshala. In today's module, we are going to discuss about lapse rate and atmospheric stability. The gaseous mantle covering the Earth's surface is known as air, which is constantly moving from one place to another depending upon the change in temperature, pressure and moisture. The atmospheric motion redistributes the mass and constituents in a variety of the complex configuration. Like any fluid system, the atmosphere is governed by laws of continuum mechanics and is capable of supporting a wide spectrum motions. Thus, the movement of air in horizontal or vertical direction is in response to the Earth rotation or pressure gradient. The transport of air in both upward and downward direction is generally governed by temperature and turbulence. The degree of stability or instability in the atmospheric system is also influenced by these conditions. It is, however, known that the air temperature decreases at higher altitude from the Earth's surface due to lower molecular activity of the constituent air. The relations between temperature, pressure and height could be established by the adiabatic processes prevailing at the atmospheric system having hydrostatic equilibrium. So, in this module, we are going to discuss about the lapse rate and atmospheric stability. What is the difference between these two? To understand the origin of different types of lapse rate, and also we will identify the mechanism for the vertical displacement of the air. We will see the atmospheric stability process and also the evaluation of the importance of stabilizing and destabilizing influences. We will also see the turbulent dispersion. Let's start with lapse rate. The Earth's atmosphere, categorized by its thermal properties, is reflected in the vertical profile of the global mean temperature. As the unit parcel of air moves vertically upward from the surface either by the action of wind or turbulence, there would be a constant fall in the temperature with increasing height. The fall in the temperature will be 6.5 degrees centigrade for every 1000 meter rise in altitude, and it is known as lapse rate. The temperature lapse rate is always positive. That means as altitude increases, there is decrease in the air temperature. And the temperature driven lapse rate is extended up to 10 km, that is in the troposphere. Beyond that, there is a sharp change in the lapse rate. Depending upon the temperature and moisture content of the air, there is also variation in the lapse rate. What is adiabatic process? Adiabatic process signifies the warming of a parcel of air by compression or cooling by expansion without transfer of heat or mass into the system. The atmospheric system is continuously governed by both adiabatic and non-adiabatic processes. In the non-adiabatic process, air near the ground surface is receiving and releasing heat in the form of short wave and long wave radiation. However, above the ground surface in the free atmosphere, the short period process is adiabatic. The upward lifting and downward descent of a parcel of air in the atmospheric system is influenced by this process. The adiabatic process is influenced by temperature differences and moisture content in the air parcel and is related to the atmospheric lapse rate. Adiabatic behavior of individual air parcel is a good approximation for many atmospheric applications. This process of temperature change is operative only in those air masses which have vertical movement. It is the only process which is responsible for the formation of all kinds of clouds. You can see in this diagram a process where the air parcel temperature changes due to expansion or the compression. Here no heat is added or taken away from the air parcel. You can see at 30 degrees centigrade, 20 degrees centigrade and 10 degrees centigrade. You can see the air parcel expands and cools as it moves up, and there is a compression and warming occurs when it comes down. Diabatic process. In diabatic process, there is a uniform exchange of heat of the air with the surrounding environment. This exchange of heat is responsible for lowering of the temperature. Diabatic process occurs only in these air masses which is either stationary or have a horizontal movement. Diabatic process of the temperature change leads to the formation of fog, dew or frost. Under these diabatic conditions, air parcel interacts with its environment both thermally and mechanically. Its potential temperature is then no longer conserved. Instead, the potential temperature changes in proportion to the heat transferred into the parcel. Most of the energy exchanged between Earth's surface and atmosphere and between one atmospheric layer and the another is accomplished through the radiative transfer. In fact, outside the boundary layer and the cloud radiative transfer is the primary adiabatic influence. What are the types of Lapse rate? There are three types of Lapse rate, which are dry adiabatic Lapse rate, saturated adiabatic Lapse rate, and environmental Lapse rate. Let's see what is dry adiabatic Lapse rate. The upward movement of an unsaturated air parcel from its surroundings takes place when affected by temperature differences. As the air parcel rises upward, it expands and there is a temperature decrease of 1 degree centigrade for every 100 meter increase in altitude. This is known as dry adiabatic Lapse rate. The variation in the adiabatic Lapse rate is dependent upon the variation in atmospheric temperature distribution. The dry adiabatic Lapse rate also varies at different levels of the atmosphere. The lifting dry air parcel after attaining condensation changes to saturated Lapse rate. You can see in this picture the dry adiabatic Lapse rate. You can see the first one, the T is equal to 10 degrees Celsius, and when it goes above or after 100 meter from the surface area, the temperature decreased by 1 degree centigrade, that is 1 degree centigrade per 100 meter, and it becomes 9 degrees Celsius. And when it moves above 100 meter to 200 meter, the temperature became 8 degrees centigrade. When it reaches 300 meter, the temperature is 7 degrees Celsius. In that way, the dry adiabatic Lapse rate is 10 degrees Celsius per kilometer. The next one is the saturated adiabatic Lapse rate. The adiabatic description of the saturated air parcel is related to the release of latent heat from condensation, which is accompanied with transformation of water from one phase to another. Usually, the saturated Lapse rate is smaller compared to dry adiabatic Lapse rate. The saturated adiabatic Lapse rate has a value of 5.5 degrees centigrade per 1000 meter rise in altitude, which is slightly smaller than the global mean Lapse rate of the troposphere. The dry adiabatic Lapse rate or saturated adiabatic Lapse rate is useful for the determination of temperature of an air parcel as it rises or sinks in the atmosphere. The lifting condensation level is the altitude at which condensation begins. When it happens, two opposite reaction takes place in the air simultaneously, resulting cooling at a smaller rate than the dry adiabatic Lapse rate. So you can see in this graph, the saturated adiabatic Lapse rate is less than the dry adiabatic Lapse rate, because as vapor condenses into water or the water freezes into ice for a saturated parcel, the latent heat is released into the parcel, mitigating the adiabatic cooling. And here you can see the temperature after 1 kilometer. Earlier the initial temperature was 20 degrees Celsius, and after 1 kilometer the temperature decreased by 10 degrees Celsius in the dry adiabatic case. But in the moist adiabatic rate, you can see that initial temperature of 20 degrees Celsius became 14 degrees Celsius after 1 kilometer. That is, there is a decrease in the, or there is a difference of 6 degrees Celsius per kilometer. In this table, you can see the moisture adiabatic Lapse rate vary with the temperatures and the pressures. And this figure denotes the dry adiabatic versus moist adiabatic Lapse rate. And here the moist adiabatic Lapse rate is always less than the dry Lapse rate. The next type is the environmental Lapse rate. The environmental Lapse rate is related to normal change of air temperature as the air parcel moves upward at a given time and place. It is generally 6.5 degrees centigrade for every 1000 meter rise in the altitude. The environmental Lapse rate thus represents the ambient air temperature with increase in altitude. One can measure the normal change in air temperature with increasing or decreasing altitude through environmental Lapse rate. And this Lapse rate changes with seasons and regions. This figure shows the environmental Lapse rate. Here, two samples of environmental temperature profile is given. One with the environmental Lapse rate 15 degrees Celsius per 1 kilometer, and in the other picture, that is other figure B, represents 5 degrees Celsius per kilometer. Here the environmental Lapse rate, here the environmental temperature profile is not always the same. We can see it clearly from these two figures A and B, where the environmental Lapse rate is 15 degrees Celsius per kilometer and 5 degrees Celsius per kilometer in the another one. Let's see what is the vertical displacement of air. The motions of atmosphere are governed by the fundamental physical laws of conservation of mass, momentum and energy. Two forces are most important for influencing the atmospheric motion. They are the body force and the surface force. The body forces act on the center of mass of a fluid parcel and they have magnitudes proportional to the mass of the parcel, while the surface forces act across boundary surface separating a fluid parcel from its surroundings. Their magnitudes are independent of the mass of the fluid parcel. The motionless air which remains under hydrostatic equilibrium is subjected to vertical displacement by force lifting. In elevated terrain, such vertical displacement of air is introduced through buoyancy and is closely related to the stability of the atmospheric mass distribution. In the event of changes in the thermodynamic state, atmospheric mass distribution is determined by gravity. The vertical pressure gradient force of the atmosphere is then balanced by the gravity. A form of mechanical equilibrium is evolved in the atmospheric system which works accurately in spite of the presence of motion. The hydrostatic equilibrium is ineffective only inside the deep convective towers where vertical acceleration overcomes the gravitational acceleration. Thus, vertical displacement of air which is controlled by thermodynamic state of the atmosphere refers to the stability of the atmospheric system. This figure shows the vertical displacement of the air. In order to determine the stability of the atmosphere, think what happens to a rising air parcel. If the parcel is colder or warmer than the environment, it wants to go down or up. You can see in this figure the temperature and against the altitude. You can see the absolutely stable atmosphere, absolutely unstable atmosphere and also the conditionally unstable atmosphere. Let's see the stability process. The stability refers the gravitational resistance of the air parcel to vertical displacement. It results from the fundamental buoyant adjustment and is determined by the vertical stratification of density or potential temperature. It also influences the dynamics of many kinds of atmospheric motions which in turn are responsible for determining the variations. Static stability is commonly represented by the square of the buoyancy frequency which plays a role in theories for flow instabilities, wave propagation and force motions. These theories apply to a wide range of spatial scales. The stability of a layer determines its ability to support vertical motion and transfer of heat, momentum and constituents. To conserve the mass, vertical motion must be compensated by horizontal motion. The hydrostatic stability therefore also influences the horizontal transport. The three-dimensional turbulence which disperses atmospheric constituents also involves both horizontal and vertical motions. Consequently, suppressing the vertical motion simultaneously suppresses the horizontal component of three-dimensional eddy motion and hence the turbulent dispersion. A layer that is stably stratified inhibits the vertical motion while a layer that is unstably stratified promotes the vertical motion through the negative restoring force of buoyancy. The buoyancy factors under stable and unstable condition reflect a conversion between potential and kinetic energy. A stable atmosphere. The atmosphere has a tendency to resist vertical motion and this is known as stability. The normal flow of air in the atmosphere is to be horizontal. When this flow is disturbed, a stable atmosphere tries to resist any upward or downward displacement and tends to return quickly to its horizontal flow. The degree of stability of an atmospheric layer is determined by comparing its temperature lapse rate with the appropriate adiabatic rate. A temperature lapse rate less than dry adiabatic lapse rate for an unsaturated air parcel is considered stable because vertical motion is damped. The stability of the atmosphere is dependent upon the temperature of an air parcel and the temperature of the environment which is expressed as DALR which is greater than ELR or TAP which is less than TSA. Where DALR represents dry adiabatic lapse rate, ELR represents the environmental lapse rate. TAP is the temperature of the air parcel and TSA is the temperature of the surrounding air. Absolute stability. Why this atmosphere is stable? The environmental lapse rate is less than both the moist and the dry adiabatic lapse rate. The rising or sinking air parcel is colder or warmer than its surroundings. The rising or sinking air parcel is heavier or lighter than its surroundings. And the parcel of air moves back to its original position. So that's why the air is considered to be stable. The absolutely stable atmosphere. The favorable conditions are temperature inversions, warm air above the cold air, the small environmental lapse rate, heating the air aloft, cooling the air below, the radiational cooling, cold advection, air moving over a cold surface, and the observed phenomenon like fog haze. When forced to rise, the stable air spreads out horizontally. The clouds which form a thin layer with flat tops and bases. These are the favorable conditions. Assessing the atmospheric stability. To determine whether or not a parcel will rise or sink in the atmosphere, one must compare the parcel temperature, that is Tp, with that of the environment, that is Te, at some altitude. If Tp is greater than Te, what will the parcel do? And if Tp is equal to Te, what will the parcel do? And if Tp is less than Te, what will the parcel do? So to assess the stability, we need these two parameters of information, that is Tp and Te. This figure shows the condition for the absolute stability in the atmosphere. This figure shows the condition for the absolute stability in atmosphere. The atmospheric stability can be observed around industrial areas when the emissions from the stack are cooler than the surrounding air. The tendency will be for the emission to resist an upward movement and to move horizontally along the stack opening. So in this figure, the conditions for the absolute stability in the atmosphere is given. The graph shows the temperature versus the altitude. Here the DALR is equal to the ELR. And in the figure 2, it shows the stable, unstable and neutral conditions of the atmosphere. Unstable atmosphere, where DALR is less than ELR, that is dry adiabatic lapse rate is less than the environmental lapse rate. The atmosphere is unstable when a parcel of air starting at equilibrium is displaced slightly upward relative to its surrounding environment. The air parcel finds itself warmer than its environment at its new altitude and therefore continues to see spontaneously away from its starting point. Thus, the degree of stability or instability of an atmospheric layer is determined by comparing its temperature lapse rate with the appropriate adiabatic lapse rate. The lapse rate greater than dry adiabatic favors the vertical motion of the air parcel and it is known as unstable atmosphere. The unstable air parcel tends to adjust itself through mixing and overturning to a more stable condition. The super adiabatic lapse are not ordinarily found in the atmosphere except near the surface of the earth on clear sunny days. When an unsaturated layer of air is mixed thoroughly, its lapse rate tends towards neutral stability. This figure shows the relationship between stability and instability in the atmospheric system. This figure shows the comparison with measured lapse rate, which is denoted by the solid black lines, and the dry adiabatic rate, which is denoted by dashed black lines. And the reaction of lifting or lowering of air parcel is shown by red arrows with respect to the temperature of its environment. Absolute unstable atmosphere. The environmental lapse rate is larger than the dry adiabatic lapse rate and moist adiabatic lapse rate. Why this air is unstable? The rising or sinking air parcel is warmer or colder than its surroundings. A rising, sinking or air parcel is lighter or heavier than its surrounding and the air parcel keeps on moving. And the favorable conditions for the absolutely unstable atmosphere are the large environmental lapse rate, cooling the air aloft, cold winds, cloud IR radiation, heating the air below, the solar heating, the warm air advection, wind over a warm surface, forest fires, etc. Conditionally unstable atmosphere. The atmosphere which has a lapse rate lying between dry and moist adiabats are said to be conditionally unstable. It is stable with respect to a lifted air parcel as long as the parcel remains unsaturated. But it is unstable with respect to a lifted parcel that has become saturated. And this figure shows the condition of conditionally unstable atmosphere. The conditionally unstable atmosphere, here the environmental lapse rate is smaller than the dry but larger than the moist adiabatic lapse rate. Here the unsaturated parcel of air at each elevation is colder than its surroundings and the atmosphere is stable with respect to unsaturated rising air. While in figure B, the lifted saturated air parcel is warmer at each elevation than its surroundings. The atmosphere is unstable with respect to saturated rising air. Neutral atmosphere. In the absence of saturation, an atmospheric layer is neutrally stable if its lapse rate is the same as the dry adiabatic lapse rate. Under this particular condition, any existing vertical motion is neither damped nor accelerated. In neutrally stable atmospheric condition, temperature structure is not static. It is continually changing. Any warming of the lower portion or cooling of the upper portion of a naturally stable layer to become unstable, and it will then not only permit but also assist the vertical motion. The dry air is neutrally stable when environmental lapse rate is equal to dry adiabatic lapse rate. Saturated air is neutrally stable when environmental lapse rate is equal to the moist lapse rate. Diurnal and seasonal variations in the stability. The stability frequently varies through a wide range in different layers of the atmosphere for various reasons. The layering aloft may be due to an air mass of certain source region characteristics moving above or below another air mass with a different temperature structure. The inflow of warmer air at the bottom or colder air at the top of an air mass promotes instability, while the inflow of warmer air at the top or colder air at the surface has a stabilizing effect. Diurnal changes in surface heating and cooling produce daily changes in stability. The amount of solar radiation received at the surface during the summer is considerably greater than in winter. Temperature profiles and stability reflect seasonal variation in atmospheric stability. The stabilizing and destabilizing influences. The stability of the atmospheric system is modified by internal motion that rearranges air. However, the overall stability of the atmosphere is external heat transfer which shapes the thermal structure. The vertical distribution of temperature provides insight into how stability is established, and it reflects the effective stratification of mass. The stability of the atmospheric system implies that a layer is destabilized by heating from below and cooling from aloft. These are the influences exerted on the troposphere by the exchanges of energy with the Earth's surface and deep space. And this figure shows the processes of stabilizing and destabilizing influences. In this figure, the A part, that is destabilizing influences heating from below and cooling from the above, while in B it denotes the stabilizing influences heating from above and cooling from below. Q is the potential temperature, Z is the height, and theta is the temperature. The stability of a layer determines its ability to support the vertical motion. It also supports transfer of heat, momentum, and constituents. To conserve the mass, vertical motion must be compensated by horizontal motion. And the hydrostatic stability therefore influences the horizontal transport. And three-dimensional turbulence, which disperses atmospheric constituents, involves both vertical and horizontal motion. Consequently, suppressing the vertical motion simultaneously suppresses the horizontal component of three-dimensional eddy motion and hence the turbulent dispersion. Convection. The vertical stability controls the development of vertical motion and hence mixing by three-dimensional turbulence. The regions of weak or negative stability favors convective overturning, which results in efficient mixing of air. This situation is common near the ground surface because absorption of the shortwave radiation destabilizes the surface layer. Introducing the moisture from below, it has similar effect. By increasing the equivalent potential temperature of the surface air, it makes the overlying layer potentially unstable. When conditions are favorable, small disturbances evolve into a fully developed convection. This figure shows the condition for the convection. The cumulus convection is favored in tropical troposphere by high sea surface temperature and strong insolation. These are responsible for large transfer of radiative, latent and sensible heat from the Earth's surface, which destabilizes the troposphere. Opposing this destabilizing influence is the cumulus convection. Reinforced by the release of latent heat, it maintains much of the tropical troposphere to neutral stability. So, in meteorology, the convection refers primarily to atmospheric motions in the vertical direction. Inversion. Inversion describes the atmospheric conditions when the temperature increases with altitude rather than decreases. Inversions result from the selective absorption of Earth's radiation by the water vapor in the air, and also from the sinking of air, which results in its compression and heating. When air is subsiding, the compressed air heats adiabatically, causing the air parcel to become warmer than surface air below it. Rising currents of cool air lose their buoyancy and are thereby inhibited from rising further when they reach the warmer, less dense air in the upper layers of the temperature inversion. In this figure, you can see the inversion. The calm winds and inversion results in the poor air quality. Here, the winter sun low in the sky, it supplies less warmth to the Earth's surface. And the second layer, that is warmer air aloft, acts as a lid and holds cold air near the ground. And the pollution from the wood fire and cars are trapped by this inversion. And mountains can increase the strength of the valley inversion. So, together the calm winds and the inversion results in the poor air quality. Nocturnal inversion. The heat transfer from the Earth's surface and convection compete for control of stratification. Their competition is illustrated by the formation and breakup of the nocturnal inversion. Strong stability near the surface that often develops at night. Arid and cloud-free condition permits efficient long-wave cooling to space. Surface temperature then decreases sharply after the sunset. To preserve the thermal equilibrium, heat is absorbed radiatively and conductively from the overlying air. This process cools the surface layer from below, stabilizing it. Strongly stable, the nocturnal inversion suppresses vertical motion. It also suppresses three-dimensional turbulence, which require vertical eddy motion. So, to conclude, lapse rate is the change of temperature with increase in the altitude. The units of lapse rate is degree centigrade per kilometer. And the adiabatic process is any process that occurs without the gain or loss of heat within the system. And we have seen dry adiabatic lapse rate, where the rate at which unsaturated air parcel will cool if it rises or warms it when it sinks. And this adiabatic lapse rate is 10 degrees Celsius per kilometer. Saturated adiabatic lapse rate, the rate at which a saturated air parcel will cool if it rises or warm if it sinks. The saturated adiabatic lapse rate is 6 degrees centigrade per kilometer. And the diabatic process occurs in those air masses which are stationary or have horizontal motion. A constant rate of cooling of the air parcel is referred to as the dry adiabatic lapse rate, while the rate of cooling beyond the condensation level is known as adiabatic lapse rate. The environmental lapse rate is related to normal change of air temperature as the air parcel moves upward, and we have seen this environmental lapse rate is 6.5 degrees Celsius per kilometer. This environmental lapse rate is the ambient air temperature with increase in height and varies with seasons and regions. The dry adiabatic lapse rate is neither dependent on the initial moisture which is present in the air parcel nor on the initial temperature of the air. The wet adiabatic lapse rate is less than the dry adiabatic lapse rate. And the static stability that measures the gravitational force of an air parcel to vertical displacement. And the stationary air parcel is characterized by stability, while rising air parcel is characterized by instability. The regions of weak or negative stability favors convective overturning. The thermal inversion occurs when layer of warm air settles over a layer of cooler air that lies near the ground. And also we have seen the thermal inversion is quite significant during the winter season. Thank you.